Hi, this is Dr. S. P. Arsa from Mechanical and Industrial Engineering Department, IIT Roorkee. I am going to present my lecture 8 here of the subject of strength of material, which is like under development of this national program on technological enhanced learning. As far as my like the last lecture is concerned, we discussed about most of the time the stress components, that actually what are the normal stress components are there, and what like the shear stress components are there, and what the direct impact is there of these like the stresses on the material. And within the material, if we want to calculate that where you see the maximum stress components is there, like if a metal is subjected by a pure normal stress, that does not mean that there is no shear stress is there. We can also get the value of the shear stress if we simply cut the plane, and if you want to calculate the sigma theta or the tau theta, that is what we discussed. And even if you see a metal is subjected by a pure the shear stress, you see means the parallel stress component, also you see we can get the normal stress component within this like the object with the shear stress component. And if a material is subjected by both the mutually perpendicular stresses as well as the shear stress component, then what the impact is there, or what the interaction is there of these stress components, and what the resultant values are there, we can also you see get those things by like the two different types of solutions which we discussed. One is the analytical solution, like we calculated at the inclined plane, or we can say the oblique plane, the sigma theta as well as the tau theta values by interaction of the sigma x sigma y in the two mutually perpendicular stresses, and the tau xy, which is the shear stresses across the plane. Then you see another solution which we discussed in the previous lecture was the Mohr circle, means you see the graphical solution, that rather to like calculate all those sigma x sigma y sigma theta and the interaction for sigma theta and tau theta, irrespective you see if we have the values of these two mutually perpendicular stresses, and if we have the value of the shear stress, we can straightway you see like plot the those sigma x tau x and sigma y the sigma y tau xy, and get the value of you see a circle, and you see just get the values of within those things. What is the coordinate of the circle, what is the center point coordinate is there, what is the outer periphery is there, what is the radius is there, and with those things you see you can pretty easy calculate that what the angle is there at which the principal stresses are there, what the values of the principal stresses are there, just by measuring. No need to calculate by analytical way, simply measure sigma 1 sigma 2, that what is the minimum point is there, what is the maximum point is there, what is the like the planes are there, the two at what angle they are like putting, and what is the first principal plane theta 1, and what is the next principal plane theta 1 plus 90. Meaning is pretty simple, you see like if we have this kind of interaction, it is pretty easy you see to calculate first, or to measure those things. And also we discussed that actually what are the drawbacks of these things of the Mohr circle. If you see if we have like some sort of the values like 25.25 or 25.47 like this kind of things, then it is very hard to draw those things, and then we need to round up the last values, and then you see like it will give you some sort of error in plotting those things even, or in measuring those things. So this kind of the truncation error is always considerable while solving stress values. So you see every like either to get the exact value by analytical way, you see by calculating sigma theta tau theta sigma 1 tau 1 theta 2 all those things, theta p theta s, pretty easy, but it is a lengthy process. For simplicity you see, but it has you see some sort of containing, either if we have a thicker pencil, then again you see like we cannot measure exact angle and all those things, so the kind of truncation errors are there. So both features are unique as far as the stress is concerned. So you see in the previous lecture, come to the main conclusion that in the previous lectures all you see we were discussing about all the stresses, that what exactly the internal intensity of the resistances are by application of the force. Okay. So now you see in the present lecture of this, we are going to discuss about that if the load application is there, then you see what kind of extension is there, because you see the stresses are there, but what the impact of the stress is, there is a deviation is there in the shape, that means there is kind of deformation is there. So how to measure the deformation, and actually how what exactly the technical term is there to measure the deformation, and then you see if we have the deformation in x direction, y direction or z direction, then what exactly the impact is, and how we can measure this deformation in x as well as y and the z direction if we have the combined loading, means the loading is there or the stress components are there in two mutually or three mutually perpendicular direction, or if only the normal stress component is there, or if pure shear stress is there, or if the combination of both the normal stress as well as the shear stress is there, then how we can measure the strains, we can say the deformation. that you see like we are going to discuss in the next lecture. And then also we are going to discuss about that actually if we are applying the load and the deformation is there, then what is the limiting like the value of the load is there through which we can say that it is the elastic deformation, or if you go beyond certain thing then it is a plastic deformation. So if you are working in the elastic deformation, then like what will be the property which are applicable only within this region, and what are the different properties which are applicable to the another region. So this kind of you see like all those properties which we are going to discuss in this particular lecture. So here it is, you see the first analysis of the strains. So you see here the concept of the strain coming from the same thing which we discussed, that if a bar is subjected by a direct load, that means you see if we have a tensile pulling, you see at the extreme corner of any bar, rectangular bar, circular bar, like that, hence the stress of the bar will like change the length. You see because of the stress, you see stress formations are there all across the structure of the this bar. Then you see like this will just tend to change the length of the bar. If the bar has an original length L, and the change of like this bar is just by an amount of dl, then the strain, which is a measure of the deformation. Okay, if you measure the deformation irrespective of whether it's a tensile load, compressive load, like there is a sort of deformation, and if you want to measure the deformation, the technical term for that is the strain. So strain can be defined by like the change of length divided by the original length, or here if I am saying that the delta L is the change of length and the L is the original length, then the strain, which is you see like the size there, which is equals to del L by L. So this is you see the technical term for measurement of any kind of deformation. Since you see strain is thus the measure of the deformation of material, and it is nothing but equals to delta L by L. So obviously it is a non-dimensional quantity, because you see delta L is also in somewhere in millimeter, meter, centimeter, micrometer, like that, and L is also having the same unit of the length. So you see both are like cancel out, so it has no unit. So strain is a non-dimensional parameter which has no unit, and it is simply like ratio of the two quantities of the same unit. That's why it is like that. So you see he come to this particular figure where we found that actually if there is you see the rectangular circular bar, if we have a circular bar, simply keeping you see like these forces at the extreme end of those things like P, extension is there, and with this extension you see the strain is nothing but equals to delta L by L. So it is, if it is a vertical part, this is the original length is there, and this is a kind of extension is there. Or else you see if we have this one extension is there, means if we have a rectangular bar which is in the horizontal direction, again if we are keeping the two same amount of load at the two extreme corner, and by keeping those things you see if we have an extension of delta L with the original length L, we can simply get the strain value that is nothing but equals to delta L by L. So this is you see the basic concept of the measurement of the deformation, and for that you see we define the technical term known as the strain. Since in practice the extension of material under any load are very small, always you see, because you see like we are putting, and there is the internal extensions are there of the microstructure, but we cannot see by naked eye. So this whatever the extension, or we can say sort of the deformation is very small, it is often convenient to measure the strain, or you see whatever the measurement of the deformation in form of the strain into 10 to the power like 6, because you see you need to magnify those things just to see that what exactly going on within the structure if you apply the load. That is you see always that is why we are always going with the micro strain, or we can see the microns of the strains when the symbol is like mu times of strain symbol. So here you see like mu times of epsilon will give you the micro strain here. Then the next point will come that actually irrespective of whatever the loading is there, what is the sign convention of the strain is. So as we discussed, you see again I just want to refresh those things, that actually whenever there is a tensile pulling is there, the tensile load is there, tensile stresses are there, and the tensile stresses are always termed as the positive stresses, compressive stresses are always termed as the negative stresses in the normal stress form. And if you have the shear stress, then if due to the shear stress, if object is tending to move towards the clockwise direction, we always use the positive sign, and if the object is tending to move towards the anti-clockwise direction like that, we are always tending to put the negative direction. Okay, so similarly you see it is a kind of analogy here, that if we apply the load and there is an extension towards the same direction, because you see the normal stresses are nothing but the axial stresses. So when we apply the load and there is an extension in that bar, these are the like the tensile strains are there, delta L because the change of length divided by the original length. So, tensile strains are always positive just like the tensile stresses, whereas you see like the compressive strains are always negative just like the compressive stresses. So, it is pretty analogy kind of that you see, and the strains defined earlier was you see like we can say the linear strain or the normal strain is there just like the normal stress component, because it is the axial strain always towards the like the same axial direction, either in this this extension part is there or the compression is there, or we can say it is the longitudinal strain because it is all along the same longitudinal way you see, because the same axis there is no eccentricity is there, wherever the load application is there it is passing through the neutral axis of a bar, and that is why you see we can say either respective it is a axial strain, normal strain, linear strain, or we can say it is a longitudinal strain. And now you see we can like the another strain which we can define as the shear strain. Shear strain is nothing but you see as the shear stress is there, it is always along the plane, means you see it is like in the normal stress the stresses were there perpendicular to the plane, these stresses the shear stresses were parallel to the like those planes are there. So, similarly you see if you want to define the shear strain, an element which is subjected to a shear stress means you see like parallel to the layers of the plane experiences a deformation, because you see if you want to twist that element from right from the across the plane you see here towards the clockwise or anti-clockwise direction, always you see the whatever the segments are there or layers are there or even the microstructures are there, they are always trying to experience a kind of deformation, and the deformation you see like it is different than the normal stress component. Then you see we need to get the tangent of that, and once you get the tangent of the angle through which the two adjacent sides are just tending to rotate relative to their initial position, always termed as the shear strain, means you see like it will just try to tend towards that movement. So, I just want to like figure out those things that you see here. If this is my object and you see here initially you see we just want to like this is the shear stresses are there the direction, and these are the complementary shear stresses are there, and these you see due to these shear stresses this object is tending to move towards the clockwise direction. You see here this will tend to move this direction, this will tend to move in this direction. So, you see we have a kind of extension at this. So, this object will move towards this direction, this object will move towards the lower direction. So, you see after equilibrium side if we have this kind of extension that it is going towards the direction, this is going in towards this direction, and then you see the respective directions are just to balance that part. If we have this phi by 2 or we can say this gamma is there, the gamma is nothing but equals to like the angle of AOB initially, the angle of AOB this and minus the angle of A dash this A dash OB. So, whatever the you see like the change is there right from first to the initial part to final part, it will give a phi means what is the change of you see the overall change is there, and this can be denoted here by the phi, or else you can say this block in fact there is a change of the shape or the strain into the like the different form is there, like you see here if we have like the point of this rigid the datum is there and we are applying the stresses across this plane, you see this is across this layer of plane. So, this is very like very much parallel to these things. So, it will tend to like move this object in this direction. So, you see if we are saying that after like stabilizing those things, if we have this kind of like the deformation like this one is shifted to this direction, this one is shifted to this direction, and if we want to measure this kind of deformation due to the parallel forces all across the plane, this kind of deformation is known as the shear strain, and shear strain can be calculated by whatever the change of length means you see here the angle of AOB minus angle of A dash OB divided by what was the original one. So, you see go back to the main position here, we were discussing that actually whatever the like the tangent of the angle which is like passing through the two adjacent side just rotate relative to their initial position, as we shown that actually they are simply trying to rotate in that way, always termed as the shear strain, which is known as by which is we can symbol by the gamma. In many cases an angle is very small because you see like always the layers are tending like they have the tendency to make a rigid base. So, that is what you see it has a less tendency to make the rotation kind of that. So, they are very small as compared to even the normal strains component, and the angle itself is like we can say that we can use these things in terms of the radiations or the radians or the degree form instead of making the tangent. So, we can say that the gamma which is equals to either A or B minus whatever the change of these things, or we can say it is of phi. So, come to the real like phenomena of the shear strain, which we discussed in the previous slide, that as we know that the shear stress is acts along the surfaces, means the parallel to the surfaces or the parallel forces are acting in that. The action of the stress is to produce or being about the deformation in any body. Consider the distortion produced by the shear stresses on an element or on a rectangular like the block is to be considerable to calculate the shear strain. Means you see we need to see that actually how the distortion is there. Means if we put the block, as you can see in this particular figure, that if you put the block here at the rigid base, and what kind of distortions are there on the top of layer. So this distortion can be easily computed with the using of the concept of the shear strain. So this is, you see, the gamma is the shear strain, which can easily find it out that actually how these upper layers are to be distorted with respect to the lower layer. So this is, you see, like which we discussed about these things. So this shear strain, or we can say the sliding of those layers from the original one, is phi, can also be defined as the change in the right angle. Means whatever the changes are there of the right angle, earlier the right angle was this shape, and how these changes are there, you see these bases is just changing like that, or the angle of the deformation gamma is then like termed as the shear strain, and shear strain is measured in terms of radians, as I told you, and hence you see it is a non-dimensional parameter, because the change of angle divided by the original angle is there, or we can say the right angle is there. Hence the non-dimensional parameter always gives you no unit, because the unit can be cancelled out from denominator to numerator. So we have two types of strains as similar to the stress, the normal strain component or the shear strain component, just like similar to the normal stress and the shear stress. Even in the normal strains also we have, you see, the different formations, like we have like the tensile strains, compressive strains are there, or even you see we have the bearing strains. Bearing strains are similar, you see, when the two surfaces are mating to each other and there is, you see, the compression is there. So what exactly, you see, like the deformations are there at the different points. If we are measuring those things, there is nothing but the bearing strains, or even if we can say that when the bending stresses are applying, means if there is a combination of the tensile as well as the compressive stresses are there. Similarly we have, like at some, if we are talking about the bending of beam, at some point there is an extension, so we can say the tensile strains are there. At some point there is a compression, so we can say the compressive strains are there. Means you see it is, if we are talking about the bending strains, it is a combination of tensile as well as the compressive strains. And the third one is the derived stress, is the torsional strains. Means you see whenever a rotating shaft is there and the shear strains are there, that means like whatever the moment which are applying at the extreme corner of these rotating shaft, we will get the shear strains at the end, or we can say it will termed as the torsional strains. And the similar, you see, the last form of the strains which we can also we can get those due to the temperature change is the thermal strains. If you see because of the expansion, if high temperature region is there and any material is which is being subjected by this kind of temperature, then always there is an expansion of the material, or there is a contraction. If the less temperature is there, lower than the melting point of that temperature, contraction is there. So whatever the change of the size of this material due to the temperature effect, these the terms, the strains which are measuring this kind of deformation is termed as the thermal strains. So you see here these kind of strains are there which are pretty similar to the stresses, but you see they are simply measuring the deformation due to the load application, or we can say due to the whatever the point of application of these applied loads are. So you see so now we have the two different terms. We have the stress because of the load application, we have the strains because of the load application. So you see both are simultaneously forming the object when there is a load application. Means you see when we apply the load in irrespective of whether it is a tensile load, compressive load, shear load, like that, there is always, you see, the stresses are being formed across the layer or perpendicular to the layer, and also the same time there is a change of the deformation. Means there is a change of the size of the element, means kind of deformations are there, or the displacements are there. So means the strains are there. So we just want to set up the relations that actually if the stresses are being formed, the strains are being formed at the same time, then what exactly the relations are there in between the stress and strains. So for that there is a basic law for in the solid mechanics, that is the Hooke's law. Hooke's law says that if a material is said to be an elastic is nothing but elastic deformation, because you see an elastic deformation, we can say that there is a kind of deformation. If you apply the load and deformation is there, once you release the load, and if body comes to its original shape without any kind of permanent set of deformation, this deformation is known as the elastic deformation. So a material is said to be an elastic if it returns to its original shape. unloaded dimensions when load is removed. Means you see, like when load is removed, we cannot realize that, or we cannot like visualize those things, that the kind of deformation was there when it was loading. We can say that this is the elastic deformation. And Hooke's law says, Hooke's law, again this is a must condition, that Hooke's law is only valid when there is a elastic deformation under any kind of loading, tensile, compressive, shear, whatever the kind of loading is there. Hooke's law is only valid when material is subjected under like the elastic deformation. Then you see, we can say that, then what is the statement of the Hooke's law? Hooke's law says that under the elastic deformation, stresses under the elastic deformation, when the load acting is there, stress formation is perpendicular to the deformation measured. Means stress is proportional to the strain. And you see, like once we like equalize those things, we have a constant. So stress by strain will give you the constant, and this constant has a real meaning. So this like this kind of constant which we are going to discuss as the modulus of elasticity. Means you see, like we have a stress, we have a strain, and if we are saying that actually you are applying the load, the stresses are being forming within the object. At the same time, there is a change of the like the length or the diameter or any dimension, and if they are proportional, means at one point of time the stress is increasing, strain is increasing, and they are proportional. And once you want to set up the relation between the stress and strains at this particular point, it will give you a new constant. That constant is known as the modulus of elasticity, because we are considering only the elastic deformation here. So you see, within the elastic limit, a material, that is you see within the limits of this Hooke's law applying, it is shown that actually stress divided by strain is constant, and its constant is nothing but equals to the modulus of elasticity. So this you see, a constant is given by a symbol E. So modulus of Young's, this is known as the Young's modulus of elasticity, because Young's like Young's was first defined this, that if you are taken this kind of material, then what is the limiting part of the elastic region is. So that is what you see for putting the limitation of the elastic region. The like Young, since Young's produces those kind of calculation, that is why it termed as the Young's modulus of elasticity, and it is always you see like denoting by E. So if you see this, the E is nothing but equals to, E is nothing but the constant, E is nothing but equals to the strain divided by stress, sorry, the like this kind of thing, or we can say it is a kind of sigma divided by the epsilon value, or we can say this P by A divided by del L by L, or we can say that actually if you put all those values together, we have the Young's modulus of elasticity, which is nothing but equals to PL by AE, or we can say this delta L. Delta L is nothing but equals to whatever the change of the length. This is the original length, this is the applied load, and this is the effective area of matter of concern. So this is you see a kind of we can say the main property of the material is there, that what the like the limiting value is there. So like this is absolutely valid when we are talking about a material ductile. Means if a material is having ductility property, then you see it can be easily expanded. It does not have to like we can say it did not show those kind of thing, like like the rupture or the fracture or this kind of property when the load application is there, and for which you see it is pretty easy for us to define the elastic region and the plastic region, okay, within these things. And for this kind of thing, the value of E, because it is defining like the region, the value of E is having a significant like importance for this kind of region dividing. So the value of E, the Young's modulus, as I told you, is generally assumed to be like same in the tension or the compression, whatever, because you see it is nothing but the stress and the strain which are there in both of the loading, the tensile as well as the compression. And for most engineering material, it has a high value, and it is almost equal to 200 gigapascal, and this 200 gigapascal generally we are using for a common mild steel. But if we are using like the high speed steel or high carbon steel, which has like high carbon percentage, okay, so for that actually it is a different value, more than this value is there. So this was the one property which was only valid for the elastic region. Then you see we have another property which is also equally important if we are talking about the stress and strain simultaneously, which is known as the Poisson's ratio. If a bar, just like you see, if you are considering those things, we have a bar you see here, and you see it is being subjected by a tensile loading, and due to tensile loading we can see the dotted region is nothing but the extension. So the initial length we can say of this bar was the firm line you can see in this figure, and the dotted line simply shows that what the deformation, or I should say it is the extension. So, if a bar is subjected to a longitudinal stress as we termed out that it is a tensile stress, or we can say the normal stress, there will be a strain in this direction, in the longitudinal direction only. So, this is the longitudinal direction, please just keep this thing in your mind, it is a longitudinal direction which is equal to sigma by E. Obviously, you see the strain is nothing but equals to the stress by strain is E. So, strain is nothing but equals to stress by modulus of elasticity, because within this elastic region only. There will also be a strain in other direction, because you see like what we are considering here, that there is a change of the length. So, the change of length is this is the extension, this is the extension. But if you go to the another direction, means you see if you are going for this direction, and if what will happen to the mutually perpendicular direction. So, if you are just looking on the top of that, we found that this one was the earlier length, and then if you look at these things after the deformation, we found that there is you see the deformation at these along these things. So, this is you see like a lateral direction. So, this was you see earlier the extension was there in the longitudinal direction, but what has happened to the circumferential, or we can say the lateral direction. So, there is a contraction here, that means if you pull the things it will extend it, but across the circumference there is a reduction is there, and this reduction like we need to measure. So, this Poisson ratio will define the relation between that towards the longitudinal as well as the lateral direction. So, there will be also like a strain is there in other direction, right angle to the sigma, and the final shape is being shown here by the dotted line. It has been observed like as we discussed, you see that for an elastic material the lateral strain is like the lateral means the circumferential part is proportional to the longitudinal strain, and the ratio of the lateral strain to the longitudinal strain, again the lateral means towards the circumference of that divided by the longitudinal where the load application is there. So, ratio of the lateral strain divided by longitudinal strain will give you a new term. Again you see it is a strain by strain, so it is a non-dimensional parameter, no value, no unit is there, no dimension is there. So, because it is a strain by strain. So, but it will give you a direct relation that once you apply a compressive load or extension, there is you see like how the changes are there, or we can say what kind of deformations are there in all the directions. So, you see here the Poisson ratio, that is also known as the mu, is equals to minus, because it is a kind of contraction is there on the lateral part. So, minus lateral strain divided by the longitudinal strain. So, again keep this thing in your mind that lateral strain is nothing but the circumferential part where the contraction is going on here in the previous figure. Longitudinal strain is that part where you see the extension is there, or where the kind of a load is applied here. So, this is the direction of the lateral divided by the longitudinal strain, and for most of the engineering material the value of mu is always like falling in between 0.25 to 0.33, but keep this thing in your mind that wherever we are applying the Poisson ratio, this is only applicable within the elastic region only. So, now you see like we discussed about the two main parameter, one was you see the Young's modulus of elasticity, and one is the Poisson ratio. So, you see like when we are discussing about the stress and strain simultaneously, then these two were the real good parameter to be introduced. Now, you see we are going to discuss about, as we discussed in the previous cases also, that if we have a stress, then what is the three dimensional state of stress. So, here similarly we have the three dimensional state of strain. So, again for that we need to consider a symmetric element. So, the symmetric element is this, you see here the like the unit cube is there, and unit cube has unit depth, unit width, and unit height is there. So, all these you see in these three directions we have the unit structures, and in that you see now we are considering the three mutually perpendicular these tensile stresses are there. So, you see here in the x axis, y axis, and the z axis you see all the three mutually perpendicular stresses, and they are in the form of the tensile. So, they are always you see trying to pull this symmetric element in mutually perpendicular directions. So, if you are saying that if sigma y and sigma z were not present, the strain in the x direction from like the basic definition we can also get simply by like the strain in x direction, this phi x psi x is nothing but equals to sigma x by E, meaning that if there is like if we have only one force is there in the x direction, axial like we have a three mutual direction which are like presenting, but if we are saying that these two loadings are not there, only the loading is there in the x direction. So, in the x direction there is an extension, and due to the extension there is a deformation which is in the positive direction. Okay. So, the strain in x direction psi x is given you equals to sigma x by E, but the effect of this, because if we are pulling the thing, then other direction will be contracting. So there is the deformation is there in other two direction. So the effect of sigma y and sigma z in x direction will be given by the Poisson ratio mu, which is equals to minus mu times, because you see if you look at those things, the Poisson ratio is nothing but equals to minus lateral strain by longitudinal strain. So that means you see there is a contraction is there in other part. So if you want to calculate the strain component in that, then we have the this psi y is nothing but equals to minus mu times of this whatever psi y is there, and psi z is minus mu times of psi z this psi z, or we can say minus mu times of this psi z value is sigma y by E, and psi z value is sigma z by E. So I mean to say that if we have only one loading, we can simply get those other values by this psi x, psi y, psi z, and we need to keep the things that actually there is only an extension in one direction, but there is a contraction is there in the other two directions. The negative sign indicating that actually if we are applying the load in the x direction, there was a compression in there in the other two directions. Even if you if you are taking the sigma y and sigma z, that means that the stresses are positive, that is tensile, they always tend to reduce the strain in the x direction, whatever the strains are there in the other the other two directions. Thus the total linear strain in the x direction, if you want to calculate, then we always go for the epsilon x is is equals to sigma x by E due to the longitudinal strain, and the other two strains are the lateral strains. So that is what you see we need to compute in the proper way with respect to the x axis. So we have the total strain, the combination of three axes are this sigma x by E minus mu times of sigma y by E minus mu times of sigma z by E. So this will give you the total strain in x direction by interaction interactive effect of x, y and z direction of the stresses. Similarly you see we can compute in other two directions also, like if there is an axial pulling is there in the y direction, so the strain in y direction will give you the sigma y by E, that is the main you see the extension, but in the extension in y direction means that there is a contraction in other two direction, which can be computed using the Poisson ratio as we have seen in the previous case. So that is equals to minus mu times of sigma x by E and minus mu times of sigma z by E. And similarly we have the strain component the z direction, while there is a loading in z direction, means the pulling is there towards the z direction, sigma as z by E minus mu times of sigma y by E minus mu times of sigma x by E. So you see we have all the three kind of the strain formations are there. The strain in x direction, strain in y direction, and strain in z direction, but to compute the strain in all three direction, there is interactive effect is there of the stress in mutually the perpendicular directions like sigma x, sigma y, sigma z, corresponding to what type of loading is. So now come to the principal strains in terms of the stresses, because you see as we have discussed already that actually there are some principal stresses are there and the principal planes are there, and if you want to compute the principal stresses and principal planes, there is there is no form of the shear stresses are. So now you see we just want to check that actually what about the principal strains. Okay, so in the absence of the shear stresses means there is no element of the shear stress on the faces of the elements. Let us say we have sigma x, sigma y, sigma z, and they are in fact if you are saying that these are the principal stresses, the resulting strain in these three directions that would always gives you the principal strains, because there is no element of the shear stresses are there to in computing of sigma x, sigma y, sigma z. So this will give you the indication of the principal strains. And we can say that actually the principal strain this epsilon 1, which is nothing but equals to 1 by E times sigma 1 minus mu times of sigma 2 minus mu times of sigma 3. That means that actually we have three different components of principal stress sigma 1, sigma 2, sigma 3, and if you want to compute with the induction effect or with the inducing of inclusion of all these three combination of sigma 1, sigma 2, sigma 3, we can easily compute the principal strain in one direction, means in one principal plane direction, that will give you the epsilon 1 which is equals to 1 by E sigma 1 minus mu times of sigma 2 minus mu times of sigma 3. Similarly we can also compute the principal strains in other two directions, other two planes I should say rather, that is the principal strain in the second plane, which is equals to the epsilon 2 is equals to 1 by E mu sigma 2 minus mu times of sigma 1 minus mu times of sigma 3, or we can say in the third plane if we are talking, and if you want to measure the deformation in the third plane, which will give you the principal strain in the third plane, means third principal plane, that is epsilon 3 is nothing but equals to 1 by E like into the sigma 3 minus mu times of sigma 1 minus mu times of sigma 2. So, there is like the analogy is there, that if we are talking about a normal stress and shear stress components, then similarly like we can go for the normal strain like the normal strain as well as the shear strain part. But if we are talking about the principal strains where there is no element of the shear strains are there, we can also compute the this principal strain component with the using of all three mutually perpendicular principal stresses are. So, now you see if you are talking about a plane stress, or we can say the plane strain. So, for that you see the third direction is gone automatically, and if you are saying that only we are working in the xy plane, where you see the sigma x and sigma y is there, or we can say the epsilon x and epsilon y is there, as well as the stress and strain components are. So, sigma z is gone, so sigma z is equals to 0, or we can say rather if you are talking about the principal stress or principal plane component, the sigma 3 is equals to 0. Then like only we have sigma 1 sigma 2, or we can say sigma x and sigma y. So, for that we can calculate like the principal strain formulations apart from those things. So, we have epsilon 1 which is equals to 1 by E sigma 1 minus mu times of sigma 2. Similarly like in other two directions also we can calculate like sigma the epsilon 2, the principal strain in other direction is nothing but equals to 1 by E this sigma 2 minus mu times of sigma 1. But now the third one, because you see like it is not there is the strain is there in the other direction also, which we need to compute because of the induction effect of these two loading sigma 1 and sigma 2. So, the principal strain in the third direction or the third principal plane, which will give you 1 by E into minus mu times of sigma 1 minus mu times of sigma 2, because mu 3 or we can say the sigma 3 is we are not considering, or maybe we can say that is equals to 0. So, hence you see like we just want to see that actually how these formations are there and how we can calculate those things. So, it is you see now we have a plane stress component, this block is there in which only the stresses are there in the x as well as the y direction. So, because of you see only the two directions are there, sigma 1 and sigma 2, or I can say sigma x and sigma y mutually perpendicular 1. So, you see like we can go straight way to this part, that sigma 3 is gone, there is no like consideration of those three, but we can calculate you see like the strain in third principal plane, which is equals to 1 by E minus like into minus mu times of sigma 1 and minus mu times of sigma 2, or we can say like the E is nothing but equals to sigma 1 which is you see epsilon 1 times E from the first formula, sigma 1 minus like mu times of sigma 2, or we can say epsilon 2 times E, which will give you sigma 2 minus mu times of sigma 1. So, if we like resolve these things, if like because the two different formations and two like the relations are there, we can simply calculate that what the principal stress formulas are. So, for that actually like we can get sigma 1 which is equals to E by 1 by E divided by 1 minus mu square into this epsilon 1 plus mu times of epsilon 2, or we can say sigma 2 is equals to like if we put these values in this particular equation, we can get like this epsilon 2 from this equation. So, epsilon 2 is nothing but equals to E over 1 minus mu square and into epsilon 2 plus mu times of epsilon 1, means you see only there is a change of that actually where this Poisson ratio will multiply. So, if you are talking about the first reason, then obviously you see now like the Poisson ratio will come into the another direction. So, you see here if you are talking about the first plane sigma 1, then obviously the mu times of epsilon 2 will give you the deformation measure, and if you are talking about the another plane, that means the sigma 2, obviously this mu times of sigma 1 will give you that what the measure of deformation is. So, it is pretty simple that actually if we are talking about like the principal stresses or principal strains, we have to be very careful that actually what kind of loading is there, and due to that what the interactive effect is there on the other two directions. So, this was you see the principal strains. Now, we are coming towards the hydrostatic, means you see hydro means the like the liquid part. So, what is the meaning of the hydrostatic stress? The term hydrostatic stress is used to describe the state of the tensile or the compressive stresses equal in all directions like within or we can say external to the body, means actually if this particular I should say if the state of stresses are being forming tensile or compressive and they are behaving exactly equal isometric way I should say in all three directions, then we can say these whatever the stresses are there, these are the hydrostatic stresses, and hydrostatic stresses causes a change in the volume, because since they are like going equally in the all directions. So whatever the change will come, the change will come in this volumetric way. That means you see dx, dy, dz, they are there, but if they are like presenting, which is you see uniform in other directions, we always focused on what the net change of these things are there, and net change will come in the volume, not in area, not in length, only the volume will take an important place to measure the hydrostatic stresses. So this will cause a change of volume in the material, which if expressed per unit original volume will give you the volumetric strain. So what the net change of the volume is there divided by original volume will give you the volumetric strain, and it can be like shown by this I times of V, or we can say, so if you want to express those things, then here we can consider again the same element which we considered in the previous cases, that we have like the uniform this unit bar is there, and all you see in all three directions we have like the stress component sigma 1, sigma 2 and sigma 3 is there in these three mutually perpendicular directions. And if we are saying that these three stress formations are equally like distributed amongst this particular among this element, then we can say like the sigma 1 or sigma 2 or sigma 3, they are absolutely apply on the principal planes, or we can say these are the principal stresses which are forming these things. And due to the application of the principal stresses, we have the principal strains, the epsilon 1, epsilon 2 and epsilon 3, they are the corresponding like the linear strain because of the application of those things. And we can say that what exactly the change is there in the x direction, we have the x plus epsilon into x, in the y direction y plus epsilon 2 into the y, and z in the z direction we have the z plus epsilon 3 into z. So now you see what the net change is there in the volume divided by the original volume will give you the volumetric strain. So come to the like the main definition, volumetric strain is nothing but equals to the increase in volume divided by this original volume, or we can say whatever the change in the volume, I should say it is a rather defined definition is there, the change in volume divided by original volume will give you this volumetric strain. So now come put those values which we got in the previous figure, that x times like 1 plus epsilon, y times 1 plus epsilon 2, z times 1 plus epsilon 3 divided by xyz, this is nothing but the original volume which will give you the volumetric strain. So we can get 1 plus epsilon 1 into 1 plus epsilon 2 into 1 plus epsilon 3 will give you like the volumetric strain. Or since these epsilon 1, epsilon 2, epsilon 3 like they are measuring in a very small amount. So if we are going in the higher order of these things, means epsilon 1 into epsilon 2 or in the square term, always you see it will give a very minimal effect on that kind of thing. So we can neglect that part, the square or as well as the multiple term, so the product term. So we have the final term as far as the volumetric strain is concerned is epsilon 1 plus epsilon 2 plus epsilon 3, means the individual measure of the strain, or we can say the deformation in these three mutual direction will give you the volumetric strain of an object. Or we can say, let us take a cuboid which we have taken in the previous case, having the initial like the length is xyz, under some load, whatever the loads are there, we have the changes in the length is dx, dy, dz. So the new volume will be x plus dx, because the x plus what are the changes there, y plus dy what are the change in y direction, and z plus dz because the change is there in the z direction. So now the new volume will nothing but equals to xyz, the original volume, into change in x direction, y direction and z direction. So xyz is the first volume. Second volume, if there is a change in the x direction, then yz into dx. If there is a change in the y direction, then it is xz into dy, and if there is a change in the z direction, then it is xy into dz. So original volume is the this xyz, and the change in volume, if you like if you replace those things, then we have this dx into yz, dy into xz and dz into xy. So the volumetric strain is nothing but the change, whatever you see the change in volume divided by the original volume, which will give you like the epsilon x plus epsilon y plus epsilon z if you divide those things. Meaning is very simple, that even if we are talking about a principal plane or principal strain, then we have epsilon 1, epsilon 2, epsilon 3, or if you are talking about like these and the normal strain and this normal plane is concerned, we have epsilon x, epsilon y and epsilon z, which will give you the volumetric strain, because you see again we are neglecting like the higher term of the strains here. Volumetric strain in terms of the principal stresses also we can compute it, because you see we can easily express the volumetric strain in terms of sigma 1, sigma 2, sigma 3. So further, if we keep all these values which we have calculated this epsilon 1, epsilon 2, epsilon 3, in this volumetric strain, we will get like the sigma 1 plus sigma 2 plus sigma 3 divided by E minus this 2 times of mu, because you see mu 1 and mu 2 is there here. So, the 2 times of mu into sigma 1 sigma plus sigma 2 plus sigma 3 divided by E, or we can say that the volumetric strain, which is also equal to, in terms of the principal stresses, is sigma 1 plus sigma 2 plus sigma 3 into 1 plus 2 times of mu divided by E. The meaning is very simple, that actually if we know the principal stresses sigma 1, sigma 2, sigma 3, we can easily get that what the net change of the volume is due to the effect of these principal stresses which are mutually perpendicular to each other, and what the interactive effect is there, or these things we can easily find it out. Now you see like again we similar to the stresses on the oblique plane, we just want to calculate the stresses the strain on the oblique plane. So, what we have earlier, we have a simple this OLMN. So, OLMN is the original, or like the unit this cube was there in the xy plane. So, this x and y plane is there, xy planes like that, and after applying those strains, now if you want to calculate that, actually if this m is shifted to m dash, if n is shifted to n dash, and you see the corresponding this L is shifted to L dash, means you see we have the new element under the application of the shear strain is O L dash m dash n dash. So, now you see we can simply compute that how these will come. This you see here the shear strain is there, this gamma xy. So, the shear strain is always coming in the picture whenever there is a deformation, or we can say the distortion is there. So, this distortion coming from L to L dash, m to m dash, or n to n dash, and we can simply calculate this part also, that what is the axial strains are there and what is the plane strains are there. And simply you see like for this kind of formation where these are forming, we can again take these things, that actually what m into m dash. So, this is nothing but you see m dash, and this another part is that means we are calculating about this particular like this triangle, and if we are imposing this triangle here, we can also say that actually what the deviation is there in the theta in like in the strain term. So, the linear strain, consider the rectangular block which we are considering OLMN, as I discussed, you see in the xy plane the strain along OX and OY, you see simple x and y direction is epsilon x and epsilon y, and gamma xy is the distortion in the shearing form. So, this gamma xy is the shearing strain. Then you see it is required to find the expression for this epsilon theta. That means you see I just want to find it out that actually what will be the strain value at the oblique plane, and for that you see again I am going to analyze this in the similar manner as we have discussed in the previous cases for the stress formation, the normal stress as well as the shear stress form in the oblique plane. So, here you see like the linear strain in the direction inclined to whatever the q part the part is there of the OX in terms of epsilon x, epsilon y, gamma xy, and the theta. So, let us you see now we just make the diagonal, you see OM of let us say length A, and now if we resolving this part, then we have the two main component in x direction ON, which is A cos theta, OL which is A sin theta, and then you see if you are saying that there is an increase in a length, so it will give you like inducing the strain component. So, the strain is in those directions, we have this epsilon x into A cos theta, because there is an x direction, and you see in the y direction there is you see like OL is there, so epsilon y into A sin theta. So, this will give you the strain in respective x and y directions. So, now you see if we are saying that due to the shear, if m is moving to m dash, then the movement of m which is parallel to x axis is this epsilon x A cos theta plus gamma xy sin theta, because you see it has both the component, it is moving towards like the parallelepiped kind of that like the structure is there. So, for that it has a variation in x direction, this direction, and this shearing direction. So, we have the component of both epsilon x A cos theta and gamma xy sin theta, and the movement parallel to y axis will epsilon y A sin theta. Thus, you see the total movement which we want to calculate parallel to OM, like since the strains are very small as practically, and we are considering always that actually if it is coinciding to the mm dash, this would be like a summation of portion 1 and 2 which is equal to, now you see here pretty simple, epsilon y A sin theta into sin theta plus epsilon epsilon x into A cos theta plus gamma xy A sin theta multiplied by this component, the resolution component A cos theta. So, if we resolve this part, what we have the strain along this particular O to M, which is equals to the extension, whatever the extension is there due to the combined effect of axial as well as the shear strain divided by the original length. So what we can do here, we can simply calculate this epsilon theta along this oblique plane is equals to epsilon x cos square theta plus gamma xy sin theta cos theta plus epsilon y sin square theta. So now if we resolve this, means if we are keeping this cos square theta minus sin square theta cos 2 theta, or if we are saying that this cos square theta which is nothing but equals to 1 plus cos 2 theta by 2, or all trigonometrical relations are there, sin square theta which is nothing but 1 plus sin 2 theta by 2. If we are keeping those things, then what we have the formula for calculating the strain in normal direction. This epsilon theta is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 into cos 2 theta plus half of gamma xy sin 2 theta. Means you see we have both the component, we have one component due to this epsilon x and epsilon y which is independent of theta, and other two components are very much dependent, or we can say governed by the theta. It is if you remind just in the stress case, that if we have the component which is under the effect of two mutually perpendicular stresses and the shear stress is there, the sigma theta at the inclined plane is nothing but equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos of 2 theta plus half of this tau xy cos of the sine of 2 theta. It is exactly similar. This expression is very much identical in the form of the equation which we defined for the direct stress at any inclined plane theta, with this epsilon x and epsilon y replacing sigma x sigma y and half of gamma xy in terms of that. So you see here it has a clear analogy that irrespective of whether if you are talking about the stress or if you are talking about the strain, always you see if you want to calculate the stress and strains at the inclined plane in terms of the normal or direct stress or direct strain, the formula is very simple and it has a clear analogy. And if you are going for the shear strain component, that means you see we discussed about the shear stress, that how to calculate the shear stress. So now you see we would like to see that what the shear strain is there to determine the shear strain in the direction of OM, because you see due to the shear strain it punctured right from the middle section. The direction OM consider the displacement of P at the foot of the perpendicular where the end point was there. So N to OM, if we simply put the perpendicular, then we will find that you see this sigma theta is nothing but equals to half of, or we can say just to put half because of the symmetricity, half of the sigma theta is nothing but equals to half of epsilon x minus epsilon y sin 2 theta minus half of tau xy cos of 2 theta, because you see we just want to put the symmetricity. So in the above expression half is there so as to keep the consistency with the stress relation, because we know that actually this tau theta was nothing but equals to sigma x minus sigma y by 2 plus half of this tau xy into sine of 2 theta. So it is pretty similar to those things, we just want to keep the consistency. So it has the same relation. Further, the negative sign in the expression occurs so as to keep the consistency of the convention, and because of OM dash moving towards the clockwise direction with respect to those things. So we are always considering that whenever the shear stress or strain is there, and if the object is tending to move towards the clockwise direction, always the positive sign is there, while OM is always considered to be negative because it is tending to move the counterclockwise direction. So you see here now the principal planes, once we know that it is a pretty analogy to the previous thing, so we can get the similar things here, that this principal plane we can get by the strain waves tan 2 theta p is nothing but equals to gamma xy divided by epsilon x minus epsilon y, and the principal strains also we can get this epsilon 1 comma 2 is nothing but equals to this epsilon x plus epsilon y by 2 plus minus. So these are the two principal strains 1 and 2, the maximum and minimum just by with the taking of plus minus sign, square root of epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 into square, or we can say the maximum shear strain also can be obtained by this gamma x by 2 is equals to plus minus square root of gamma epsilon x minus epsilon y divided by 2 whole square plus gamma xy by 2 whole square. So it is pretty simple, because as we have already derived for the stress formulation, so there is nothing to be discussed here, because it has already been discussed that it is pretty analogy, those kind of thing. So now you see if you are coming towards the plane strain, because you see in the shearing we found that actually it has a combined effect and distortion is there. So in a xy plane three stress components are there which can be easily viewed, that if you are talking about the x part, the normal strain component towards the x direction, we have the epsilon x even in the vertical direction, if the normal stress component, the strain component is there, then epsilon y is there, and this is you see the shear strain because of the plane strain part is there. So these three figures clearly shows that actually what kind of the displacement or the distortion are there in corresponding relations. Therefore, a strain at any point in a body can be characterized by two axial strain, this epsilon x in x direction and epsilon y, and a plane strain, that is the gamma xy as a shear strain. In case of the normal strains, the subscript you have used to indicate the direction of the strain, that means like the epsilon x or epsilon y means the direction of the change in the x and y direction respectively, while you see like the gamma xy, the shear strain, it has two like the subscripts. One is the single, means the first subscript, single subscript notation is not practical as we shown, because it is a plane strain, or we can say it is always there towards the xy side. So we need to concern both the things. The symbol this gamma xy gives you like the two main formation, one is the x and y, or we can say the y of x. If the element is pretty symmetric, we can say it is pretty easy to describe the symmetricity because of the this either the nature of the force as well as if the nature of the what the geometry of the shape, or we can say geometry of the object is, or the shape of the object is. The shear strain gamma xy is always considered to be positive if it represent the decrease the angle between the sides of the element of material, which is like lying in the parallel to the positive x or y axis. That means you see if it is decreasing in the angle towards that, we always concern the positive side, while you see we can think of like the positive shear strain produced by positive shear stress, and the like again if we are talking about the negative shear strains, that means there is an increase like the angle between the sides of any element material which is lying parallel to the x or y direction. That means you see we can simply conclude those things, that actually if you are talking about a plane strain, that plane strain is is not associated with the plane stress as such. You see plane strain is basically associated with the three dimensional stress conditions, because in the plane stress we are simply concerned with the two directions, while in the plane strain we can go for all three directions like that, and that is why you see it can be defined by the components of this the epsilon x, epsilon y, and this gamma xy, because you see it is in the all three directions like that. So we can say the plane strain conditions associated with the three dimensional stress system, and the plane stress is associated with the three dimensional strain system. So in this chapter we discussed about that what the strains are there because of the application of load is, and if the strain, if we are pulling in the one direction, then what are the corresponding changes are there in the other directions, and if you want to relate those things, then the Poisson ratio is an important factor, and also the Young's modulus of elasticity is to be defined for the elastic region where the stress and strains are proportional to each other. And then the last part you see we found that if you want to calculate if a material is subjected to all three kinds of strains, then the strain at inclined plane is exactly similar to the stresses at the inclined plane, and it is pretty symmetricity. So now you see in the next lecture we would like to discuss about that how to resolve these issues, because this analytical part is pretty simple, but what about the Mohr circle. So the next lecture we are going to discuss about the Mohr circle for the strain component. Thank you.